So yes, pleasure to be here. Thank you, Volker, for letting me introduce our work, motivated by the ARC challenge, which I have been talking about for 1.5 years or so, and 2 years actually by now. And so I will start this talk with the ARC challenge, but then I want to really go a little bit behind the ARC challenge and say, okay, what is the motivation of the solution approach that we are trying to pursue, which is really about how humans probably try to solve this challenge. And so let us start with the, the ARC challenge itself. It has been quite a ride on this challenge, introduced by François Chollet, a left top here person, in 2019, where he was a software engineer at Google, basically, and DeepMind, and has more worked on software projects, really. But he was much inspired by developmental psychology and has developed this challenge motivated by conceptual primitives that are believed to exist in babies by the first year of age about. This was the original motivation. On the left, you see the first type of challenge, ARC version 1, where you might guess it, right? But you can see you essentially need to guess, okay, how does this matrix convert into this matrix? What's the logic behind it? That's always the ARC challenge. You get a couple of tasks and see before, after matrices, and the goal is to find out, okay, what's the rule, right? So here in that first problem, it's relatively simple, right? You might see it now, by now, right? Things fall down, right? So it's, and we can just express it as humans in saying things fall down, right? But already that is like a quite abstraction and conceptualization, right? That has unfolded in our minds in some way or the other. But let's go back first to the ARC challenge a little bit. This was the task 2024. There were $600,000 in prize money. Nobody got it. And now last year, 2025, we had the ARC version 2, which was expanded and more complicated. And now we are on ARC version 3. And let me introduce those, and in fact, lo and behold, now we are on prize money of $2 million. So there is quite an interest. François Chollet is talking with OpenAI and Altman and stuff about these things, and has made a huge fuss about this. This is not a joke anymore, as it was 5 years ago, maybe to some of us, basically. Yeah, there's big money involved here. It's a little bit scary even in some sense, yeah. But let's look at a couple of tasks first to see what this is all about, yeah. So here you've already seen this task, I already explained. So you have before, after matrices, and then you have 1 or 2 or 3 test matrices usually that your program or your mind or whoever needs to create the output basically for it. So this is relatively easy. This is a task I will get back to over the talk. So here you basically see these columns in gray, and they are recolored, and there's some recoloring logic here somehow, right? And now you might still debate in your head what it is, and one or the other, then maybe you realize, okay, the smallest one, it gets yellow, the second one is green, red, and blue, and so you also know that this would be yellow, green, red, and blue on a different situation, and that's what we have done in our minds, right? There are more complicated tasks already in version 1. We have like fractal-like tasks sometimes, yeah. So here you basically, the bottom one is gives you the overall structure, and the top one shows how each pixel is converted into a 3 by 3 or 6 by 6, no, 3 by 3. My vision is not so good in that transformation, right? So this was version 1, and then in the end of version 1, nobody solved the task. There is also a compute limit to a certain extent, but LLMs were not particularly good in it. Maybe I jump ahead briefly and show you the situation of the leaderboard of mainly version 1 tasks in September 2025, where it's September 2024, November 2024, that was still like all below 50%. So a year later, the GPT models got much better. And if we look then to the, maybe first, human performance is on 95, 98% when you take the time. There was a Turker movement here. The average Turker 2 years ago was on 76% or something. But if you take if you take your time and you get into these problems, you can solve. Not all of them maybe, but 98% or so, I would say. And the other ones you have to talk to your friend briefly, and then you also solve it. The other one usually. Yeah. But then the ArcAGI leaderboard now, 19th of May 2026, is basically more or less solved by Gemini and co. Yeah. On the other, though, we see a little bit here on the x-axis, you see the compute that needs to be invested in this, and this is still, if you go $1 per task of compute really to solve this, our brain is still more efficient than that. Yeah? But nonetheless, interesting developments. Yeah, this is just over 2 years. Basically, we have jumped from LLMs not solving this task basically at all to now this version 1 tasks solving them. So, but what happened then is basically that we jumped to version 2, and this task got a little bit more involved. More complicated. Here is again a recoloring task. Basically, one also sees this relatively quickly, particularly because I've primed you with other recoloring tasks. Notice, yeah. But nonetheless, the recoloring here is not as clear directly. And if you look longer, you see, okay, it's the number of holes, and the number of holes gives the rule of the recoloring. Just a couple of further impressions. Here, it's basically objects that you perceive as objects, red things that you perceive as connectors, and you need to connect those objects together to the central yellow object. So more complicated chain of thought, right? An algorithmic structure kind of that is in the head, or a process structure that is in our head to solve these tasks. There are also other tasks. It's not all about object manipulation. There are tasks like this one, where you have kind of a flow process unfolding within the object, within the interior of an object. The interior essentially starts to expand outwards and then kind of spreads also diagonally in that regularity that it's pushed out. Yeah? So it's a clear pattern regularity here that needs to be inferred, and it's also not a take one object and place it somewhere, but it's really a process that you need to kind of simulate. At least we would simulate this process, and it's also a natural process of a fluid kind of expanding, right? But you see how these things can be have a large variety of problems. Yeah, one last one for version 2. Very involved one. In fact, we have talked about this one in the lab a lot, so some of us are smiling now. Yeah, it's so we basically, if we briefly look at this, right? So we see, okay, this is kind of the background, and on this background there's something placed. Yeah, the right side is the background, but notice in the test there's not the right side is the background, but the central side. So also a more generalization necessary here, right? And you place something on the background, and the placing, then you might notice, well, okay, this shape, or this shape, or this shape, right? I detected here the red one, here the yellow one, so the single colored thing kind of is that determines the shape on the right side, yeah? But we still have a fractal component in this shape. Each cell of this shape, essentially each cell of this shape becomes this whole 3 by 3 blob. And lo and behold, this 3 by 3 blob is still inverted by color. Yeah. And lo and behold, where do we place this object now? We place it aligned to the lower right, to the upper left, to the upper right. And we still rotate this object according to this kind of rule here by 180, 90, or minus 90 degrees. And also this rotation generalizes here in this test. You have like rotations, this one that has not been seen in the training. Yeah? So much involved. Yeah? This is clearly a tough algorithmic structure to find, yeah, out of nothing. Right? But nonetheless, the big companies have been busy, and we can see here a snapshot of the ARC leaderboard of version 2 of on lo and behold March 2026. Yeah, 70 something percent, and if I go now to May 19th of today, we are there at about 85, 88%, but not above 90% supposedly human experts that learned to solve this task. And one could probably say that these LLMs, Gemini here, GPT-5, they were all trained on this task too. Yeah, they were all hardcore trained on this task and similar tasks, right? Because it's $1 million challenge, and they haven't solved it yet, right? So it's so they are also trained on this task, right? But and they don't reach quite 90% yet. So there's still something out there, yeah, that's not quite really grasped by LLMs. And and lo and behold, the newest task, ARC3, which is deadline somewhere in this fall, $2 million prize money now, is now a little game task. And it's also interesting, this snapshot I took like about half a year ago or so, when the first problems came out. Now this looks as fancy as this, yeah, to sell the tasks and make them attractive and so forth. Yeah, so now we have a little Nintendo like game console, yeah, where we play this, and I want to briefly show you how one plays this thing. So let me see if I get this right. Yes, so we can see here now the game, and if I press start here, you just have this console, yeah, and you basically see, okay, you can press these buttons. And now if I press the button, so I press the up button, for example, you see this effect. Yeah? And I press the up button again, I see this effect again. I press the left button, nothing happens, except for the energy goes down if I press left. So it's energy. Yeah? We've uncovered the energy level, yeah? But where is it from, right? We just interpret it this way. And then I move maybe a little bit further on. And let's move, I move there, oh, and it basically, nothing happens, but the lower left thing flashes up. So a wonderful event signal, right, that basically, okay, this thing might probably need to match in shape. Yeah, maybe it matches in shape, but how can I change the match in the shape? So basically, well, how can I do it? I mean, I have a free area that I have uncovered by now, right? There's this free world that I can move in, this maze. And so let's move through the only position that is still interesting in this maze, right? And so, whoa, now I have changed that thing. And so lo and behold, we realize, well, the only interesting position in the maze still is where I can change this stuff. And so basically now let's move maybe back to this thing, and then wow, I have cleared the level. Yeah. So and now, right? Notice, right? How this game out of a pixel space, right, has turned into a game for me, right? Where I need to move my little agent that has this weird shape and color, right, to the goal, but I can only move it into the goal location when the shape that's there matches the target shape, which I have at the left bottom. And lo and behold, it seems like I've not played all these games and so forth, but it seems like that as a human, you are basically able to solve these games at first go, without any instructions. Huh? How is this possible, right? And now it's basically a fact. Now, if I move this back here, and let's go back to the talk. Here we go. Now, where are we in LLMs on this task? There. Yeah? Notice the axis. Top is 3%. Yeah. And so with 1,000 investment in reasoning, they are on 3% on this task. Yeah? So nice job of the consortium that is running this ArcAGI to identify a subspace of problem domains where we humans have a lot of intuition, a lot of understanding of rules that we just build up, and that makes us intuitively able to solve these tasks, right? So of course, the big question is, why do such tasks come so natural to us, right? I mean, sure, we are all gamers here or so, more or less, like some more, some less. We've played with computer games and so we have like some cultural bias to be able to solve these tasks, right? But still, I mean, it comes very natural to us, right? It seems very clear, right? And so mind the cultural predisposition, clearly, yeah? So, but nonetheless, right, I would argue that essentially our world is full of arc-like tasks. Yeah? Our world offers locally regular contexts. Yeah? Just have a look briefly at this situation here in front of me, right? There's tons of stuff that is not relevant for me really right now, right? But nonetheless, it is a stable local context, right? There's nothing moving here when I don't interact with it, right? It's a stable situation, yeah? And in that stable situation, I need to, in order to move the slides or show you how this game works, so I only need to focus on a particular subcontextual structure in this stable contextual environmental space. Yeah? It's just the laptop, the screen, right, and the windows, how they are, and how the Zoom streams this panel here. So if I shift things over, they should be visible in Zoom and so forth. So that's just my contextual frame that I'm in. This is my subcontext that I'm in. And this is the claim that I want to make today, or that I want to delve deeper into, right? That our minds form contextual frames. And these contextual frames, this is a new term kind of that I'm trying to use to make sense of this, basically, is basically as a behavior and predictive model of the chosen subcontext that is currently relevant for me. Yeah? I have behavioral primitives. I know where to press to get to the next slide. I know how to use my mouse to move the windows around and so forth. Yeah, these are my behavioral primitives that I can interact with this subcontextual world in this particular situation. And I argue you all have your subcontextual worlds in your minds right now. You might just listen, but you might also make notes, right, and so forth. And so you have your subcontextual world. And this is the contextual frame. And the argument is that our minds pursue tasks within this subcontext. Yeah? So our minds do two things. They always infer the contextual frame, the subcontext within which we currently believe we can solve our tasks. And then we do the planning within this subcontext in order to solve the tasks. Yeah? That is the big claim, essentially, that that is unfolding, right? So we need behavioral policies or action decision making on the meta control level to structure our task space, to structure the context that we are currently believe to be in, or that makes us focus to solve tasks, and then another control process that basically decides how to navigate in this contextual subspace to solve the tasks. Yeah? Now, why do we do this? Well, I have hinted this already, but just as a reminder, right? the world is the foundational prior of all of this, essentially. Yeah? The world has space and time, and so naturally it has localities. Yeah? This is physics, essentially. Yeah? This is a fact. Yeah? So basically, if I show you like an illustration of this, right, our world is full of stuff. Yeah? Maybe not as full as this image, yeah, but actually, if you think about it and zoom out kind of a little bit, if you look into a city situation, yeah, there's a lot of stuff going on, right? And we can now zoom into any of these little situations, like these guys don't only stand there, but they're dancing there around in the circle, right? And here is some baptism going on. Haven't noticed the little squirrel there on the tree that's happily doing something, whatever, yeah. So there is a lot of subcontextual structures, and this is determined by the spatial temporal locality of our environment. Yeah? There is just spatial temporal localities, yeah? Because things do not just swivel around like crazy, but they can only move locally and interact locally with each other. So basically, local regularities is the environmental context. Yeah? An environmental context is locally stable, inevitably, due to physics. Now, our world is full of such local environmental contexts. Yeah? However, there's more around us than what is relevant to us. Yeah? So all these things that's around me, only what is relevant to me. So I need to build, as a human, a frame. I need to solve the frame problem and decide what is relevant. Yeah? And in order to solve this, I form contextual frames. And what is relevant depends on my inner needs. What do I want? What's my current desired goal? Yeah? And, of course, on my bodily abilities. So there's clearly grounding in our bodies. Yeah? Sensory motor grounding is part of this story. What I want to essentially propose, right, is that, as I hinted at already, right, we construct like an internal context or contextual frame, a contextual frame within which we make behavioral decisions. But now, in some disciplines, this is boring because context was always relevant, and so, sure, what do you tell us about, right? So there, of course, this is not an answer. This is just basically raises more questions, right? The questions, and the main questions maybe are what drives its construction and how do we make behavior decisions within these contextual frames that we are shaping and forming all the time. And I want to motivate this from a very recent paper that I got aware about 3 years ago, Reverse Engineering the Centered Self, just came out on Psychological Review, actually, from the Tenenbaum group, a couple of others, Ullmann, Paul, and also his name Cédric Collard from the French side that moved to MIT, I think 2 years ago. And they are claiming one fundamental core function of cognitive action choices, right, can be essentially framed like this. This is a snapshot from their paper, this equation also. So just to see how they highlight this and how important this is to them. So what they're saying is basically, okay, I make action decisions, choosing the best action. How? Choosing that action that maximizes the expected utility of what happens in the world, essentially, for myself. Yeah? And they put here the environment as the world model, so of what I believe happens in the world, yeah? As the state and actions that are unfolding in the world. And now I will try to translate this now into my contextual frame perspective, essentially to show now that the environment and the utility of this world model function, of this action choice function, essentially emerge out of the principle of minimizing anticipated surprise. Yeah? And that is basically what we're going to. So let me try to formalize this a little bit without hopefully losing too much time here. But basically, right, we basically have, I just translated the equation into a utility function, and the model function is still exactly the same equation here. Yeah? And I just want to basically point out that that behavior should be executed as believed to maximize expected utility. Clear in the utility function essentially gives some sort of value function, right? It's probably a Q value function on RL, like value function essentially that's behind this, right? And I want to translate this now a little bit into a latent state here, because I argue that this model now is not really a reactive or predictive model just on the state space, on the pixel space in the arctask or so, but we lift this to a conceptual space, a latent space, right? Objects that move around. And this is that latent space that I will add into this equation now. This is this L here. And so with that latent state, we can make value predictions, and with that latent state and actions and state estimates of what's going on in the environment, perceptual states, we can predict how these dynamics unfold in the environment. And note that because the model, right, and this is from the Tenbaum group already, right, that this model, because it's inside the utility function, right, the model essentially itself gives the interpretation of the world that I use to estimate utility, right? So that's really important. It's not like a separate thing or so that there's a predictive function that unfolds and then there's a utility function, but the utility function is the input, the model function. So that's really the trick here also from these guys also that I think is really important. And so the purpose of the model thus, because you want to maximize utility, right? So the model needs to structure in such a way that it helps maximizing utility, right? So the model has not the purpose to predict the environment per se, it only has the purpose to predict the environment in such a way that I can anticipate utility better. So this is really, really important, I think, to realize. So, but what we are arguing now in my lab is basically that, well, this predictive model needs to be contextualized. It cannot be just working on like pixel space or on an S space. There's this latent space that is the interpretation of the world that must be maximally effectively interpreted to predict utility. So if we solve the arctask, right, what does this mean, right? We want to represent the arctask in such a way that I know how these transformations unfold, where they come from, right? How that in the simplest way of translating the arctask. And we argue basically that this model has two particular components to it. A contextual frame representation that essentially says the control structure, how I do my inference, and then the actual behavior representations that decides how I really infer my behavior within this structure. And this model function can be split up in further components now in order to realize this. And this is a habitual behavioral component that basically gives my behavioral tendencies in a particular task, pressing this button, so forth, driving my bicycle in a certain way, right? Any behavioral primitives that I have as part of my model as action space, shapings basically, and then the predictive model components that are the perceptual component, the transformation component, and the contextual frame component itself. So basically that you can actively meta-control like infer the contextual frame within which you try to solve a task. Within that contextual frame, perceptions unfold and predictive transformations, how these things develop over time. And I have habitual prior behavior to check my action tendencies, how I would interact with this world. And with a predictive model, I can then roll out, do planning basically, and see, okay, what would happen if I do this? And is this really, depending on my goal, what I really want to happen? So basically, with this structure, I can do perceptual inference, action choice inference, and contextual frame inference. And so, this structure is already relatively complex. We essentially, it kind of looks, maybe first a visualization briefly. So it looks kind of like this. So we have a contextual frame that I infer, and with that kind of umbrella or this frame, I basically have my perception going on. I do action decision making with my predictive model. I predict the output, and then I compare, is that where I want to go to? And that allows me to do planning and inference. But now the question is really, Okay, now maybe, sure, this model sounds plausible, sure, great, but how do you learn such a model? And what we have uncovered over the last years or so is basically that we can learn such a model just by the principle of minimizing anticipated surprise. Yeah? And the minimization of implicit surprise is nothing else, right, as negative log probability of reaching my goals given the current state in my situation. And I can also project this to the perceptual side. I also want to minimize my perceptual surprise, but only for the purpose of minimizing my goal predictive anticipated surprise, really. Yeah? So you can do a derivation there out of this. And with Max over there, we have uncovered this wonderful derivation here that basically says, well, if I want to minimize surprise of my goal state, essentially, so I want to make sure that I reach my goals, if I have actions in the middle, yeah, and I have given my goal and I have given my state, and I have a Markov blanket situation, and I can essentially infer the posterior over actions in that Markov blanket structure. Yeah? And I can, and if I want to do this, and I want to minimize surprise, linking this with the action basically in this equation, yeah, maybe I don't go through the derivation, right? But what happens is nothing else as here we get like kind of an elbow bound out of here, yeah, that consists, but this is not an approximation or an upper bound, this is exact derivation, yeah, and this is basically the goal of minimizing anticipated surprise basically plays out in the goal of minimizing anticipated surprise under the expected action densities that I infer, yeah, in the goal-directed way, under the cost of changing my action prior to my action posterior under the consideration of reaching a goal. So I have like a cost-benefit trade-off here that just pops out of this structure, basically. Yeah, that is, I want to maximize or minimize the error, maximize the likelihood that I reach my goals with the least inference effort, with the least density changes in my mind, yeah? With the least belief changes in my mind. Yeah? And when I integrate this now into the contextual frame structure, basically we have the context and we have the belief state, then basically this develops into context dynamics that are informed by my sensory interactions over time. And this whole development essentially can be, as I will show now over the next couple of slides, be continuously adapted over time. So basically, I will show that this is a process that not only unfolds at a particular here and now, but it just unfolds continuously over time by just doing inferences with a focus of minimizing anticipated surprise. And how is this possible? Well, if we start at some point, basically, I get next thing here, I get the current perceptual sensory input. So I get my posterior over S, over my state estimates, given my prior context expectations and my prior previous state expectations. Yeah? And then I can do the next inference process, and basically I just infer now my action, my goal-directed action, which is nothing else as because given my goal where I want to reach, so I assume this as given, and I have my Markov blanket here again with the action being inferred given the context, the latent state estimate S, yeah? And this should be S, sorry, and the outcome here. Now it's S again. and now I can do this next thing. I see the outcome, the sensory perception, so I get my actual outcome, and I can do a Markov blanket inference given the outcome here, basically. The sensory outcome, yeah, sensor is always given here, basically, we are sensors. Then I get the outcome. And finally, if I have done this inference, I can essentially take the context as my Markov blanket shielded by the previous context and the current interpretation of what has currently unfolded. Yeah? And so I can optimize my action, habitual priors to habitual posteriors that are goal-informed, essentially, and I can optimize my model predictions by the outcome-informed model predictions as a context. So the context tries to essentially form a structure that is optimally structured for task-oriented behavioral decision-making and world representations. And that can continue forever, and so we have basically just a dynamic cognitive inference dynamics unfolding over time in our minds that basically is doing contextual inference and action inference and perceptual inference in interaction with each other over time, always shielding things with a Markov blanket to have optimal posterior inference. Yeah. So it's always latent state as inference, perceptual inference, action, monitoring the outcome, and then inferring retrospectively a contextual state that would have been better to represent the whole thing that currently unfolded. Yeah. And then I can do this over time. Yeah. So yeah, here comes the lots of this has been inspired by Max's work with a very concrete model. Also prior work on this or related work from Johanna, who's also here. Chris has done some previous work on this, and lots of other people. All of my lab has inspired me, really helped me to do this. But let me see one concrete example now of a particular model that is now fully tuned in context representations on a particular task, which is the Stroop task. So I hope I can explain this, but we now have this structure, and we basically say this is our cognitive model that does Bayesian inference by minimizing anticipated surprise. And now we put this in this task, and basically latent state representation is just the word encoding and the ink color encoding basically in the Stroop task. And the action prior is essentially, well, read out the word, yeah, which makes sense because you usually have to read out words all the time. Oops. Can we mute all maybe? So this is the action prior, and the action posterior then essentially takes into consideration, well, do I do the right thing? If I read out the word blue, it's like, oh wait, no, this is wrong. Yeah, I need to say red here. Yeah, so basically I take the action posterior by doing Bayesian inference, and we can show, which I don't cover in this talk, that this Bayesian inference can in principle be computed in closed form, but in principle you can also do this by rejection sampling or other kind of sampling basically that can progressively approximate the posterior by more and more sampling basically. Yep. And this number of samples that you need until you converge to a threshold degree, we take as reaction times in this model. And so what we essentially show is that by essentially overruling your possibly incorrect prior in an incongruent task, it's an incongruent task, you basically have to change your belief prior over actions, which in particular context might say just read out the word, right? To the action posterior by realizing, no, your task space, your goal space is really to say the ink color, to tell the ink color. Yeah? And this is the cost basically, and the green is the benefit of getting it right. And so we see basically, while I change my action prior belief to posterior belief, I basically progressively have a higher likelihood of getting the goal right, or my error decreases essentially. And my cost of inferring the posterior progressively increases. The more I sample, the slower my posterior changes, because I have already a lot of evidence, right? So that's why it's not exponential here, really, the cost rise. But at some point, the cost overrules the benefit, and I should stop and do the reaction time. Yeah? And lo and behold, with this basically, and with the contextual model involved, you essentially can model the typical proportion congruency effects, also task switching effects and item-specific congruency effects, and so forth in in this Stroop task and also in task switching relations and so forth. So clearly I cannot give you all the details in this talk, but the point really is that we build a 4-level hierarchy, a contextual frame primitives that basically say habitual behaviors or task-specific situations, or what is the outcome correct or incorrect. The contextual frame, that is basically composition of contextual frame primitives, so just primitives. The parameterization of this frame, and action control. These 4 processes unfold, and I have simplified a little bit in that contextual graph structure, and that basically leads to the anticipated surprise, minimizing anticipated surprise as the core objective, which infers perceptions, actions, outcomes, and contextual frames, as I have shown. So relating this back to the original equation, we have behavior choices essentially made by inferring a contextual frame which defines behavioral primitives, perceptual primitives, goal primitives, and using this frame as the current world model. So also outcome primitives I should have put maybe. And then perceiving the state of the world within the frame, planning goal-directed interactions within the frame, and estimating plan utilities within the frame by essentially trying to minimize the cost-benefit equation that I have shown before. So I hope this kind of gave you now an impression of how this may work on the contextual frame side and what drives the construction minimization of surprise in this hierarchical 4-level structure. How do we make behavioral decisions within it? Well, by estimating goal-directed posteriors. But now, what does this all have to do with the arc and the real world? Now, I hope I have probably lost some of you. So with the last couple of slides, I want to relate this back to our approach to solve the arc challenge and what this really means in the real world. So let's look at one task. Remember this task from the beginning of the talk, and so we basically say, okay, we have a contextual frame, and now basically for an arc task, right, my latent space is not this ink color and word representation, right, and my outcome is not only correct or incorrect, but yes, the outcome is basically the matrix, really, and my internal contextual spaces are conceptualized, right? They contain particular concepts. So when I face a current task, I infer relevancies. I infer concepts, entities, spatial relationships, event schemata, right? Properties of objects, like its height or something like this that I focus on. And then when I realize the height is important, basically height is locked into my contextual frame and say, well, okay, here's height is here relevant. So let's remember height, yeah? and process it for the individual task, right? And so I kind of give a domain-specific language, right? My contextual frame, it essentially kind of defines the domain-specific language, as it's sometimes called, yeah, or the language of thought within which I currently think in. And we infer a sequential interaction schema, a chain of thoughts of behaviors, essentially interpreting these bars in a certain way and so forth. When facing then a current trial, right, when I check my algorithmic manipulation that I want to do for the individual trials, I basically check, well, is it really the right order? Is the yellow one in both cases the smallest one, right, and the least height one, and so forth, and so I can instantiate it trial by trial. So really when I'm solving this task, I would claim basically, well, the objective function is minimizing anticipated surprise. That essentially means like I want to explain away outcome perceptions. Right? I want to minimize the surprise of these colored bars, basically. Right? That's my goal. Right? It's my task here in this arc task, right? And it's as good as I can express it in words. And so kind of I want to minimize the description length of these outcome representations, I can say, yeah, in some form. Yeah? Some representation, some surprise measure of the presentation, so on the pixel space, another one. But if I now construct a contextual frame to minimize this objective function, right, I first might identify foreground, background. It's relatively easy here, right? It's just black background and colored foreground objects. They are gray in the input and they are colored in the output. So I realized I can think on the object level, particularly because these objects seem to match in the input and output, right? Their outlines stay the same, their shapes stay the same, but so they kind of match one-to-one to input-output, it seems, right? But if I probe now object manipulations, where I see, well, I need recoloring, right? These objects I can match in one-to-one, but there's some recoloring here involved. So recoloring concepts come in. We all have a recoloring concept in our head, like coloring an object in a certain way, right? But which color? Well, kind of leads to an internal inquiry, like a subcontextual situation, right, where I basically have a pairwise matching between these individual objects, matching them with colors. And then I might essentially identify that ordered height matches with color. And then I basically say that see that there must be a parameterized event schema, which is recoloring, and I map essentially the ordinality in respective to height to color, and that is what I'm doing then in the end, and that is how basically I can also solve this final task. And when I show you basically, this is kind of what our algorithm also identifies, which is of course relatively difficult to read, but I have individual nodes here, and we have the input, the target node here is the yellow one, oops, and the blue one here is the input node, and you can read this basically, so you basically find the background color first and identify what's foreground and background. And then basically you identify here single colored objects then, and then I think the pathway here that got connected. Then you gain pair embedded objects that basically links to the objects that you have identified in the output. And you basically say, they match with each other. And so that allows me to probe like a recoloring or some other process across all these object tasks. And so basically in this case, this node here essentially is doing that. One cannot really see it, but I can. Yeah, so it's basically does for all objects in the input. It does recoloring, and the recoloring logic here is a little bit hidden in this node, but essentially it learns to recolor this, thus producing exactly those objects that had been identified on the output. So I have lifted the output also to the conceptual space objects, see that they are colored objects, and then you paired them, and then you realize, with the forward recoloring logic, I can create just these objects as output, essentially explaining away the recolored output objects by generating them from the input objects with the logic of ordinality being the coloring. Yeah? So this is what this algorithm has found, in fact, and I have run it just 2 hours ago and let it sit here for you. The process takes about 10 seconds or so to create this graph, or 20 seconds maybe. Yeah. So, so far so good. Now I hope I come to the end in a minute. Just one last word about the ARC3 task now, right? So here basically it is maybe even more complex, but it goes in a similar direction, right? You have to lift this pixel space task into a conceptual frame, a contextual frame task, where you essentially have identify for this task now, but how general can this be, right? That there is a free space that you can roam around. What is your agent that you're controlling? What are interaction points? And so forth. So you have actions in the world which are directional keys which move the little agent. The predictive world model says about action consequences. When can you move to the goal state? When can you manipulate the shapes? The goal representations really you need, right? What is really clearing your level? So moving into this goal position when it has the right shape and later also the right color and so forth. And then potentially extended action options like finding shortest path might be possible, but once you have this lifted into this conceptual space, in this contextual space kind of this problem domain, right? Then you can do the planning within, and that is what I'm claiming our brain does anyways all the time, and that's why it comes relatively easy to us to learn to solve such tasks. So in conclusion, I hope I could show you that contextual frames are very useful. They also alleviate cognitive effort, because if you think about, there's so much in our world that we could think about all the time. So we need to focus on the stuff that's relevant, frame problem. Contextual frame inference essentially invokes an internal environmental model, this contextual frame, also habitual behavior primitives and task-specific goals. And with this situation, I basically kind of have a POMDP problem, yeah? An internal contextualized Markov decision process problem that I haven't touched upon so much in this formalism today. And as a result, a human-like problem-solving behavior should emerge when we model interpretations of the environment in this way, and then really problem-solving behavior within these interpretive spaces, which I call contextual frames. And well, as Volker has mentioned in the beginning, I guess I also am much interested in AI. So, not only how the human brain does this. So basically, I think artificial systems really need to actively contextualize their latent state. So if they do that, if they do this efficiently, then they can generate human-like adaptive behavior, but they can also avoid subtle and unpredictable errors because they're fully focused on the local causality that's currently relevant. They can save much of energy because they don't need to compute all the correlations that they have in their huge systems or huge models, but can focus that and probably develop AGI in this way. And clearly, this might be a crucial step towards AGI, and I always like to end with a word of caution. I think this has huge potential. Maybe Europe will go ahead before the others on this way. It's saving energy, hey guys. But who knows? But I think this has huge potential, but of course it can also outsmart us in many ways, and so yeah, we should be aware of this too. And this leads me to thank my cognitive modeling group so much for interacting with me, bearing with me, and discussing many exciting things and sharing ideas and exchanging them together. Great pleasure, and thank you for all of your attention.